Unit 2, objective number 3. Now, back in objective number 2, it was how to solve an absolute value equation. Objective number 3 is how to solve absolute value inequalities. We're going to begin with a less than on problem number 1. 2 times the absolute value of x over 3 plus 5 plus 1 is less than 19. Now, just like in objective number 2, the first step is isolate the absolute value bars, which simply means anything that's not in absolute value can go away. So we're going to subtract the 1, and we'd have 2 times the absolute value of x over 3 plus 5 is less than 18. Now the next step would be divide both sides by 2, and we'd have x over 3 plus 5 still in the absolute value bars is less than 9. Now we're going to have to do something a little different. Since this is a less than, I tell my students to make what I call a less than sandwich. We're going to put the x over 3 plus 5 between positive 9 and negative 9. And the way we're going to write it is like this. Negative 9 is less than x over 3 plus 5, which is less than positive 9. And now we're just going to solve both sides of the problem at the same time. I'm going to subtract 5 from both sides. And I have negative 14 is less than x over 3, which is less than 4. Now, the last thing I'm going to do is I'm going to multiply both ends by 3. And that's going to give me negative 42 is less than x, which is less than 12. And that actually is my answer right there. This is telling me that all of the values of x that are sandwiched between negative 42 and positive 12 can be plugged into this inequality, and the answer will be less than 19. Now, sometimes they want the graphic solution of that just on a single number line. So I made just a simple little number line with 0 right there. I need negative 42 on this end. I need positive 12 on that end. And the way that I show that all the values of x between those two numbers, but not including those numbers, can work is like this. I just connect them like that. So that's how a less than works. Now I've taken the exact same equation in example 2, but I've turned it into a greater than problem. So I'm not going to go through all the steps again to isolate the absolute value bars. They're the same steps. Subtract 1 and you'd have 18. Divide by 2 and you'd have 9. So that would leave us to this position right here, is greater than 9. Now, at this point, we're going to do something a little different since it's a greater than. We're going to do case 1 and case 2, just like we did on objective 2. Case 1 would simply be x over 3 plus 5 is greater than 9. Now, case 2 would be x over 3 plus 5 is less than negative 9. Now solve both of these inequalities. Subtract 4, and you'd have x over 3 is greater. Subtract 5. Subtract 5, sorry about that. Subtract 5, and you'd have x over 3 is greater than 4, and multiply both sides by 3, and you'd have x is greater than 12. That's your case 1 answer, all x's that are greater than 12. Now the case 2 answer, subtract 4 again, x over 3, sorry guys, I have no idea, subtract 5. So x over 3 is less than negative 14. Multiply both sides by 3, and you get x is less than negative 42. Now we join those two answers with the word or, and now it's time to graph those answers. So all values of x that are greater than 12 or all values of x that are less than negative 42. Now, if you look at the two graphs, remember they were the same problem, only one of them was less than and one of them was greater than. The less than one produced an answer that is what I call a bounded region. All the values of x between negative 42 and positive 12. The greater than actually produced answers that can be found in one of two regions. Either all the numbers bigger than 12 or all the numbers less than negative 42. Now, there is a special case you need to look out after, and this can be a little tricky because in Objective 2, anytime you had an absolute value equal to a negative number, you knew it was no solution. Well, this time you got to think a little bit harder about it. Absolute value of x is less than any negative number, in this example, negative 3. Well, this would be no solution. Because whatever number you put in absolute values are going to turn positive. And a positive number can never be less than a negative number. But for the exact same reason, there's a different answer here. Absolute value x greater than negative 3. Well, this one's going to be all real numbers. Or maybe some teachers want it like this, always. When is the absolute value of x greater than negative 3? Well, it's going to be always. Because whatever you put in there, the absolute value bars are going to turn it positive, and a positive number is always greater than a negative number. In our second set of examples, we're going to take the same kind of problems, absolute value inequalities, but we're not going to solve them from an algebraic viewpoint. We're going to simply solve them from a graphing viewpoint. So in this first example, I've got f of x as the function 1/3 times the absolute value of x plus 2 plus 3, and I've got g of x equaling the constant of 5. And we're going to graph and indicate the solution to where f of x is less than or equal to g of x. So the first thing we're going to have to do for these things is we're going to have to graph them. So the f of x function is an absolute value function, so you know it's going to make a v. The vertex of that absolute value v is negative 2, positive 3. And the slope to get to the next points are up 1 over 3. Up 1 over 3, and I'm going to do it one more time. Up 1 over 3. And then do it the same the other direction. So those are enough points for me to have a really good idea of where that V is going. So there's the f of x function, and I'm going to label it f of x. Now it's time to do the g of x function, and the g of x function is simply a constant, g of x equals 5, so it's a horizontal line that goes through y equals 5. So here's the g of x function. Now, in the last objective, we looked at where they were equal to each other. So what we really cared about was the shared points, the two places where they intersected. This time, we're actually worried about where is f of x less than or equal to g of x. So where is the f of x function, the blue v, lower than the g of x function, which is the black straight line, horizontal line? Well, it's in all of this area right here. The f of x function is below the g of x function for all values of x negative 8. So negative 8, and we're going to put less than or equal to x, which is less than or equal to, this x value is 1, 2, 3, 4. And graphically, that's the answer to this problem. For all values of x between negative 8 and positive 4, that's where the f of x function is less than the g of x function. For example number 2, we switched it to a greater than function. So we've got new functions. F of x is 2 times the absolute value of x minus 3 plus 4. So the vertex of this v is at positive 3, positive 4. The slope to get to the next point are up 2 over 1. I'm going to do it one more time. Up 2 over 1, up 2 over 1. And that's enough for me to know where that v belongs. There's my f of x function. Now the g of x function is a constant at 6. So it's a horizontal line that goes through y equals 6. So there's my g of x function. Now this is just saying where is f of x greater than or equal to g of x. So it's saying where is the f of x function, the blue function, above the g of x function. Well, it's actually in 2 different places, this place and that place. So this one is represented by all x values that are greater than or equal to 4. That would take care of the one that goes out to the right, and the one that goes out to the left would be all x values that are less than or equal to 2. Now, you would get the exact same answers if you followed the algebraic techniques that I showed you a couple of minutes ago. But this is the way to do it if you're asked to solve by graphing. Let's end objective 3 with the special cases. Now, the special cases can be a little tricky if you're trying to solve them using algebra. But if you're trying to solve them graphically, they really make a lot of sense. So on this last example, I've given f of x to be 3/4 absolute value x minus 1 minus 3. And I've given g of x as -5. So before we even look at what we want to do with them, let's graph them. F of x is an absolute value graph with a vertex at +1, -3. With a slope of up 3/4. So there's my f of x graph. Now my g of x function is -5. G of x equals -5, which is a constant, which is a horizontal line that simply goes through y equals -5. So there's my g of x function. Now I can ask the two questions. Number one, where is the f of x function less than the g of x function? Where is the f of x function below the g of x function? Well, it isn't. So there's no solution. Now, if we turn the question around, where is the f of x function greater than the g of x function? So where is the f of x function above the g of x function? Always. Or all real numbers. And with that, that closes off objective 3.